Alrighty. So this talk is Modern Python, Better Python, because it's about using newer features of Python to improve our code. But other titles were possible. For example, and I really mean this, the horrors of my earlier code. I hate some of my earlier code, and the title's appropriate because I first got the idea for this talk when I started rebuilding the open source SOFA statistics project from the ground up. The DNA of SOFA statistics was set in 2008, and many of the building blocks I take for granted in modern Python to improve readability just weren't available then. The result has been a lot of code that I don't enjoy maintaining. Another title could be Shrink the Think, because the talk is largely about programming as a mental activity and ways of reducing mental load. This is the structure of the talk, which I'll show again as we pass through the content. You'll see it again, don't worry. Let's start by defining better. There are lots of ways in which code can be better or worse. Performance, correctness, readability, brevity, extensibility, and more. But here the focus is on readability. Better code for the purposes of this talk is code that is easier to understand. All right. Okay, so now that we've defined better, we can think more clearly about what was wrong with my earlier code. The first thing to note is that my older code actually worked. Sure, it was often hard to understand and often painful to make changes to, but it did work. And in a strictly technical sense, it was maintainable, albeit only with considerable effort and sustained concentration. Unfortunately, even though I tried really hard to improve names and documentation, there were fundamental weaknesses in how the code was organized and the data structures I used. Let's look at some of those weaknesses and possible remedies. In general terms, the biggest problem was the sometimes extreme level of concentration required to follow its logic. It was very easy to get lost and confused. Instead of this, it often felt like this. It was a struggle to get my brain to clear the hurdles my code imposed because of the way it was organized. The main problem with my SOFA code was that it didn't have a tidy narrative. Here's an example of what a simple narrative might look like. Get data, validate data, standardize data, analyze data, and send report. And the lower level here, the nested level, also makes sense. Another problem was bad function interfaces. It was hard to get an overall sense of what was expected by functions, what was returned, and how things glued together. A good interface must not only work, it must also make sense. Here is an illustration of a messy interface. You have to look at it for a while to work out the overall logic. If we strip out the type hints, the interface is less noisy, but now we have even more questions about how it works. Here is a much better interface. There are far fewer moving parts, and if the meaning of something isn't clear, it is easy to see the design of the objects and any associated documentation. Note, this is demo code only. Most real code will have lots of attributes, doc strings, and so on. And don't worry if you don't understand the details of these data classes. The main point here is that it is easy to drill down and see what is going on. Here we can see that the data has a title, label value pairs, and a count of the number of records. The style has 3 colors, and the output is a title, a path to the chart generated, and a message about the chart. Our guiding principle should be shrink the think. As it says in the Zen of Python, readability counts. And readability matters a lot. Well-written code is easier to maintain. It's much quicker to load the meaning into our brain, so we can actually do what we came to do. For example, fix a bug or add a new feature. Readable code frees up mental capacity for solving higher level issues. For example, perhaps we should consider a completely new architecture or try using a different library. And well-written code just feels better. So good readability also makes it much easier to assess correctness Is the program actually doing what we want it to do? There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. That's a quote well worth revisiting from time to time. Our goal here is code so readable that it is obvious that it is correct. In short, readability matters because programming is all about the human brain. If we can shrink the thinking required, we no longer require mental perfection to get good results. Well-written code is more likely to fit into our brains in one go, which is important because the human brain is variable in its performance. Our effective brain size is sometimes compromised by factors like open plan offices, staying up late watching Netflix, meetings which break our mental flow, and in a team context, there will be significant differences between individual team members. It's complex, but one thing we can be sure of, readable, well-written code will fit in more brains more of the time. To some programmers, this might feel like pandering to weakness or inferiority. If that's you, think of it as a technical challenge like any other technical challenge. An analogy might help. With computer processors, there is a huge difference between just fitting within main memory and not quite. If the content doesn't quite fit, then the operating system has to manage virtual memory and swap content back and forth. If you're really unlucky, the system will start to thrash, with most of the effort going into memory management and not much into doing the actual processing. Now, human memory is much more complicated, but the general point holds. If you can shrink the thinking required, you can get major improvements in mental performance. And even if you are smart enough to understand the code in ideal circumstances, it is not always possible to avoid less than ideal circumstances. So we should do everyone a favor and make sure we write readable code. So what features can we use in our Python code to improve its readability? In particular, I'll look at type hinting, data classes, str_enum, and add note. Now, I'm not saying that using these features will make your code readable or that your code can't be readable without them. The argument is that these new features make it a lot easier to make readable code, especially when the problems being solved are complex. Let's start with type hinting. Type hinting started off as a complex mini-language. It was easy to dismiss as a hobby horse for static language extremists. But the syntax has become much more streamlined, and if you were originally put off, you should give it a second look. We can make the correct usage of functions more obvious by including type hints when we define them. So in this example, our getCoord function tells us that it expects a string label, the coordinate parts are floats, and what it promises to return is a coord object. The general rule is that readability should be the guide. Use type hints if they prevent confusion and add confidence. Modern IDEs can identify type errors. For example, you return a set when you promised to return a list. And this feedback from the IDE can be useful without being intrusive. Type hinting started in Python 3.5, but it has improved enormously since then. For example, union has become a lot nicer, and this is just one of many examples. We can just use a pipe to show acceptable alternatives, the bit down the bottom. In this case, we can expect either a string or none back from the function. Type hints themselves need to be easy to read. This is an obvious point, easy to read if they are to improve the readability of the code, if that's your purpose. Then there's data classes. When data classes were first introduced, I didn't think they were very useful. I was 100% wrong, largely because of a framing problem. I saw data classes as something that had a very specialized use case in object-oriented programming. I now recognize their value for creating named, documented data structures. Data classes come with other benefits as well, but for the purposes of this talk, the big win is code that is easier to read and understand. When data is structured rather than just collected, so a list just collects things, for example, When it's structured, we should prefer tuples over lists because there's less flexibility for things to go wrong. And we should prefer named tuples over unnamed tuples. Dictionaries might also be an option, but data classes are probably the best solution generally because they are good for both simple and complex use cases. And the transition from simple to complex data classes is gradual and flexible. It is possible to add more robustness and sophistication as and when required. Here's an example data class. At its simplest, it consists of a name and some boilerplate and the actual content. It's pretty self-documenting, although you can also add an explicit doc string. It's easy to add simple defaults, but it's also possible to add much more complex ones. For example, a different UUID for each instantiation. It's easy to add type hints, and it's straightforward to add validation, derived values, a nice string representation, which is especially handy for debugging or logging, and convenience functions, for example, for importing or exporting your object. Using data classes for more of your function arguments and outputs can make code a lot more readable. Good interfaces make it a lot easier to build complex things. Data classes make it a lot easier to change interfaces too. It is easy to identify all cases where a data class is used, unlike general-purpose Python data structures such as nested lists, tuples, dictionaries, and so on. You can just find all cases where you use that data class. And changes are often breaking changes. For example, adding a new attribute might break existing code, and this is a good thing, part of the fail hard, fail early principle. It makes it easy to identify all the places that need alignment with the new design. Try doing that with a general-purpose dictionary. Changes might not be evident until runtime, if then. That's because complex, general-purpose data structures are flexible to a fault. Their greatest strength is their flexibility. Their greatest weakness is their flexibility. If you don't need complete flexibility, then you're free to choose a data structure that is documented, named, and has some guarantees. Now let's look at str-enums. They arrived in Python 3.11. It was possible to use str-enums earlier than 3.11, but it required dual inheritance. Str-enum is now a first-class citizen and incredibly useful. Here's a simple example. Enum is part of Python's standard library. In general terms, enums are programmer-defined options that all belong together and have a named group, in this case, city. We can use str-enums with dot notation, and our IDE can help with code completion. Whether to use a str-enum or a plain string depends on whether the string represents a programmer-defined identity or not. If it is an identity and we don't really care as much about the string content, which we might even swap out at some time, we can use str-enum. If the text is not an identity, we can use a string. In this example, if I'm using 2 degrees as an identity, I'd probably have a telco str-enum. If I'm using the content of strings, such as 2 degrees or 2D or something like that, perhaps when searching for text, I would use a standard string. Str-enums have many benefits. They make it clear which options are expected and possible. Str-enum clarifies the context for strings. We can avoid confusing person name and area name. And str-enums are great in type hinting because they let you know the collection of valid strings that can be supplied, what you're expecting. The final feature we're looking at is add note, and that's quite recent. Errors and exceptions are something we often have to deal with under stress. Anything we can do to make exception messages more readable and helpful, the better. This is where add note is really good. It creates more readable, or lets you create more readable messages than making and raising a fresh exception. Exception notes are an opportunity to add context and helpful detail. You can even add advice or steps to undertake to fix the problem if that is possible. Now, it's super easy to forget to re-raise the enriched exception. You really need to do that. So make sure otherwise you've sort of handled it without handling it. Okay. In summary, to simplify our code, we need to increase the amount of code by using more features and their boilerplate, and we require extra knowledge of those features. We simplify by adding more and requiring more, which is paradoxical. We've probably all heard the slogan, less is more, but sometimes the paradox is that more can be less. More code equals less mental load. Another paradox is that sometimes strict constraints and the enforcement of guarantees creates lightness and freedom for the programmer. This is because, when done well, such restrictions reduce complexity. There are numerous examples in the physical world where these sorts of paradox apply. Trains can't deviate from their tracks, but in return for this restriction, they can travel extremely fast and efficiently. You can only put standard-sized containers on ships, but in return, you get massive economies of scale with specialized equipment and interchangeability. Okay, so now let's look at the difference better code can make. Here is a highly simplified version of one of the code flows inside my original SOFA statistics project. You don't need to read it to get the point. It was orderly but confusing, and I'm saying that as the person who wrote it. There was a lot of leaping about in my code, and remember, this code actually worked, but still, it had big problems. A lot of leaping about in the code, and it was very easy to lose context. As mentioned earlier, it was correct code. There are doc strings and attempts to name things well, and each function describes what it does, but it fails at a higher level. It can't be stitched together into a tidy summary narrative. To understand it, you have to follow all the pathways without getting lost. In contrast, in the newer SOFA Lite project, I made a conscious effort to use modern tools and define things with the narrative in mind. Once again, don't try and read all the words. I'll provide an overview. The main point is that there is an overarching narrative. We start with the GUI, which produces some data and display-related settings and values. Data extraction happens down one path, and configuration such as styling, down the other. In the data extraction path, we get the actual data and then create a data class. In the config path, we create a style data class and pass through a few other settings. Combining the data, style, and a few other config settings, we create an output data class. That output data class has a method enabling it to generate HTML. At each stage, we have a clear sense of the input we want to receive and the output we want to produce. The net result is code we can easily follow. Care was also taken to ensure that each lower level made sense with its own internal narrative. This process was iterative. If I wasn't happy with the higher level narrative, perhaps it was too complicated, I'd rethink it and then refactor all the subcomponents to align with the simplified narrative. Given the reliance on data classes, this was quite manageable in practice. If I couldn't name something or describe it easily, I viewed that as something to fix. Here you can see some more of the doc string I showed earlier. Don't worry about trying to read it. It's just an illustration. The point I'm making is that the documentation in the code captures a bigger narrative and then demonstrates it in action for something concrete. In this case, for making pie charts. Down the bottom, you can see we are building an intermediate charting spec. In particular, a chart category frec specs data class. And here you can see the function tasked with actually making that data class. There are clear names for incoming variables, and they have type hints. There's a str enum defining the sort options. There's a type hint for what we're trying to build and return. And that's our target, and it's easy to see its docs. Admittedly, the code you see here is not exactly simple, okay? It is doing a complex task, but it is now at least manageable. The mental load is a lot lower than would otherwise be the case, and we can concentrate on bridging the gap between what is supplied and what is required. Those are both well-defined. And it's reasonably easy to grasp the purpose of each bit, which is what we focus on further down in the function when we actually build what gets returned. And at every sub-level of our data class, we have a similar, clearly defined, name-rich target. Once again, we can focus on clearly defined tasks, getting from clear inputs to clear outputs. We're not just leaping about and hoping we load enough into our memory to actually work on it further. We can also jump to the code defining our data class, for example, and get a really good idea about what it is, possibly why it is the way it is, how to use it, and so on. Fortunately, we can choose how we want to use the new features in modern Python. Python lets us make the trade-offs that suit our needs. Perhaps we're making a small script, or perhaps we're building a massive code base that will be worked on by multiple people over many years. Type hinting is optional and flexible, so we have options there. Strict enums and plain strings are usually interchangeable. We can use data classes or fall back to tuples, lists, and dictionaries. We can use add note or craft our own exceptions to raise. But these are all tools we should probably have in our toolkit. Because good coders are always open to better ways of doing things. Good coders have a learning mindset. Fortunately, Python provides a low barrier to entry for using the new features that enhance readability. Increasingly, I find myself using data classes, type hinting, and add note in even some of my most simple scripts. And I also use a lot of strict enums, albeit mainly in my more complex projects, which is why I think we need to make these tools part of what we could call common Python, features we might hope all Python programmers will know and use. The good news is that modern Python makes it easier than ever to write human-readable code. Now, I'm not saying, once again, that these features will make your code readable or that your code can't be readable without them, but using them should make it a lot easier to write readable code, especially when the problems being solved are complex. I'll end with a call to action. Start using data classes, stop using named tuples, and so on. Start using strict enum when strings are about identity. Use type hints where it improves readability and helps the IDE. Use add note and f strings to improve the debugging and logging experience. And think more about providing clear, logical interfaces and narratives which glue it all together, and then document the main things. So in conclusion, use these modern Python features to shrink the thing and make your code more robust, maintainable, and pleasant to work with. Now, we have time for any questions.
Could you just summarize the difference between a class and a data class?
Just summarize what it is?
Yeah, summarize the difference between a class and a data class.
Yeah. Okay. One of them, they're a bit weird in a way. But what they enable you to do is get rid of a whole lot of boilerplate. So you'd go usually dunder in it, and you have a whole lot of attributes you're going to pass in, and then you go self blah equals that attribute and so on. And all that boilerplate, that's done for you by a data class. That's the first thing. The second thing is you've got some things baked in like dunder post init, which is code which will run as soon as it's initialized. So it's a good place for validation, for example, where you go, wait a sec, that's not in New Zealand, that's a coordinate from somewhere else, and you raise an exception. It's also when you use a data class, you're signaling to someone that this is about the data. It's really about the data, and you're all the methods and functions you're adding are sort of very data oriented. So like a representation of the data with dunder str, maybe import export functions, maybe derived values from that data. It's still very sort of using a, say, property decorator. It's all very closely coupled with the idea that this is about data. Yeah. But you can see that that very question threw me off when I was considering it. I didn't see it as being a sort of a nice data structure that could replace named tuples. I didn't sort of see what I was seeing until later.
Hey, thanks, Grant. I am curious. You used docstrings very heavily for actually writing your narratives. Have you ever felt the pull to create or to use some sort of richer documentation system like Sphinx or what have you to be able to describe what your intent is with the code that's slightly separate from the code itself?
Yeah. Yeah, I actually use Sphinx quite a lot on an earlier project. At the moment, I'm only able to work on SOFA-Lite in a very small burst of time, which is why I've had to really concentrate on making it. So I go, I have to get from this input to that output, and I don't have to think about side effects or anything else. But I sort of haven't really decided to do a whole lot of other stuff around the project because I'm actually concerned, is it going to come to a stop, as I have other things to do in my weekends. So that's sort of the true answer. It may be that I should consider doing other things as well. Yeah.
Regarding type healings, do you think ending type healings and apply strict type checkings is the norm among the Python community? And do you think that modern Python projects should enforce type checkings using tools like MyPy or PyWrite?
Sure.
Thank you.
Yeah, it's the question sort of really very much about sort of a dilemma around type hinting. Are we using it as documentation and guidance to communicate things about our project and to pick up some obvious errors, like I'm returning a set instead of a list? Or are we using it for a more thoroughgoing sort of static type checking type thing? And I think the answer to that depends on what product you're making and what your priorities are. I know there's, I don't know if Tim's in the audience here or not, but not another Tim Penny. But anyway, he gave a talk about type hinting that was really quite sophisticated. So I think it's an option within Python, and I think it should remain an option. There should be that flexibility within Python for pumping out a quick, well-written script that achieves some end, and making a very sort of like enterprisey, mission-critical type thing where you're using everything in the arsenal to make sure it's correct.
I think we've got time for one more question.
Hi.
Yep.
Yeah. Just my question is related with the when you need to get from point A to point B. For instance, you have the raw data, and then you get your final data, and you make many intermediate objects. Have you come up with any strategy with prefix, suffix, labels that allow you to distinguish between one and the other and keep the narrative?
Yeah. It's funny because I gave a talk last time about, I think it was about organizing code into folders and submodules and how to make that work. And the main thing is you've got to be able to make quite radical changes to how you organize things without losing a lot of time. And so being able to quickly and confidently rearrange your modules and substructures and rename things, break your data classes, and then in all the places they occur, fix them and align them with the new design, means that I can, anytime I have a sort of a niggling sense that things don't make sense, that the flow doesn't, it's hard to explain, which is a bad sign. I go, this would be better, and I don't hesitate to then go and break everything and fix it, because I know I'll be able to achieve that without getting confused. Whereas in the old SOFA statistics, if I'd even dared to attempt such a thing, it would have taken some sort of continuous day of concentration to even dare to attempt such a thing, so I didn't get confused in the middle or lose track. That's sort of an answer.